Deep in the cosmic abyss, 13 billion light-years away, something impossible is happening. A black hole, one of the most violent and mysterious objects in the universe, is doing something that, according to our best physics, simply cannot be done. It's growing. Not just growing, but devouring matter at a rate that's 2.4 times faster than the absolute maximum speed that the laws of physics allow. This isn't a minor measurement error or a statistical anomaly. This is a fundamental violation of cosmic law, like watching a car exceed the speed of light or seeing water flow upward. For over a century, astrophysicists have relied on certain unbreakable rules about how black holes behave. These rules aren't suggestions. They're mathematical certainties, carved into the very fabric of space-time itself. But this ancient giant from the dawn of time is treating our most sacred laws of physics like suggestions. What we've discovered doesn't just challenge our understanding of black holes. It threatens to topple our entire model of how the universe evolved from cosmic infancy to the rich tapestry of galaxies we see today. The impossible has happened, and science is scrambling to explain how.
To understand why this discovery is so earth-shattering, we need to dive into one of the most elegant and fundamental principles in astrophysics, the Eddington limit. Picture a black hole as a cosmic vacuum cleaner, pulling in everything around it with gravitational force so intense that not even light can escape. But here's where it gets interesting. Black holes don't just swallow matter silently. As gas and dust spiral into the abyss, they heat up to millions of degrees, creating an accretion disk that glows brighter than entire galaxies. This superheated material doesn't just fall quietly into the black hole. It screams. It radiates energy outward with such intensity that it creates radiation pressure, a force that pushes matter away from the black hole, fighting against its own gravitational pull. Sir Arthur Eddington realized in 1919 that there's a perfect balance point. Pull too hard, and the radiation pressure becomes so intense that it literally blows away the very material the black hole is trying to consume. It's like trying to drink from a fire hose. Past a certain point, the pressure just pushes everything away. This maximum feeding rate, the Eddington limit, isn't just a theory. It's a mathematical certainty based on fundamental constants of nature. Breaking it should be as impossible as creating energy from nothing, until now. When we look deep into space, we're literally looking back in time. The light from distant galaxies has traveled for billions of years to reach us, carrying snapshots of the universe's youth. The James Webb Space Telescope has become our time machine, peering further back than ever before, to when the universe was less than 1 billion years old. What we found there broke our brains. Supermassive black holes, monsters containing millions or billions of times the mass of our sun, were already fully formed, sitting at the hearts of galaxies when the universe was practically a cosmic toddler. This was already a problem that kept astrophysicists awake at night. Think about it. These black holes had to grow from something. Maybe they started as the first generation of massive stars that collapsed. But even if you begin with a black hole containing 100 times the mass of the sun, and even if it feeds at the maximum Eddington rate without pause, there simply isn't enough time in the young universe for it to grow into a billion solar mass giant. It would be like finding a 1,000-year-old redwood tree in a forest that's only 50 years old. The math doesn't add up. The timeline doesn't work. Scientists proposed exotic solutions. Maybe these black holes formed directly from primordial gas clouds, bypassing the stellar phase entirely. Maybe they found ways to feed more efficiently than we thought possible. But we never imagined they might simply ignore the speed limit entirely. The discovery came from an international team of astronomers using data from multiple space telescopes, combining observations from Chandra X-ray Observatory, the James Webb Space Telescope, and ground-based instruments. They were studying a quasar, essentially a supermassive black hole's accretion disk shining across cosmic distances, from when the universe was only 1.5 billion years old. At first, the measurements seemed wrong. The team rechecked their calculations, recalibrated their instruments, and ran the analysis again. The result remained stubbornly impossible. This ancient black hole was accreting matter at 2.4 times the Eddington limit. To put this in perspective,
Imagine a highway with a speed limit of 65 miles per hour, based on fundamental laws of physics, not just traffic safety, but on the actual structure of reality itself. Now imagine clocking a vehicle traveling at 156 miles per hour on that same road, with no apparent modifications or special conditions. The black hole wasn't just slightly exceeding expectations, it was obliterating them. The measurements showed X-ray emissions and spectral signatures consistent with matter falling into the black hole at this incredible rate. The energy output was so intense that it should have created radiation pressure powerful enough to halt any further accretion. Yet, somehow, the feeding frenzy continued, unabated. This wasn't a measurement error or an observational fluke. This was nature flipping the bird at our most cherished physical laws. The scientific community responded to this discovery the way any rational group would when faced with the impossible. They scrambled to save their theories. The first hypothesis involves super Eddington accretion flows, exotic feeding mechanisms that could theoretically allow black holes to exceed the classical limit. Perhaps the matter isn't falling in uniformly, but in highly collimated streams, or through magnetic field configurations that somehow bypass the radiation pressure barrier. It's elegant, but requires very specific conditions that we've never observed before. Then there's the direct collapse scenario. Instead of forming from stellar remnants, maybe some early black holes collapsed directly from primordial gas clouds, creating seed black holes that were already massive enough to grow rapidly, even within normal limits. But this still doesn't explain how they're feeding so voraciously now. Some researchers suggest we're witnessing episodic feeding, brief periods where black holes gorge themselves at super Eddington rates, followed by longer quiet periods. It's like cosmic binge eating. The radiation pressure might take time to build up and push matter away, creating windows of opportunity for rapid growth. But the most unsettling possibility is that our fundamental understanding is simply wrong. Maybe the Eddington limit applies only under certain conditions we haven't identified. Maybe there are exotic physics at play in the early universe, different densities, temperatures, or even modifications to general relativity itself that we haven't accounted for. Each explanation requires us to either discover new physics or admit that our models of cosmic evolution are fundamentally incomplete. Neither option is particularly comforting for a field that prides itself on mathematical precision. The universe, it seems, has been keeping secrets. This isn't just an academic curiosity, it's a full-scale crisis for cosmology. If black holes can routinely exceed the Eddington limit, then our entire timeline of cosmic evolution needs to be rewritten from scratch. Consider the implications. Galaxies form around supermassive black holes. Their growth rates determine when stars can form, how gas flows through cosmic structures, and even how elements are distributed throughout the universe. If these black holes have been growing faster than we thought possible, then every model we've built about cosmic evolution is potentially wrong. Dark matter interactions, early star formation, the timeline of reionization. All of these processes are intimately connected to black hole growth rates. Change the speed at which black holes consume matter, and you change the entire story of how the universe developed, from a smooth, nearly uniform soup of hydrogen and helium into the rich, complex cosmos we inhabit today. We might be looking at the cosmic equivalent of discovering that human civilization developed twice as fast as all archaeological evidence suggested. Every assumption, every model, every carefully constructed theory about our cosmic past becomes suspect. The universe has just handed us a puzzle piece that doesn't fit anywhere in our carefully assembled picture of reality.
If one ancient black hole can casually violate fundamental physical laws, how many others are out there doing the impossible? This discovery opens a terrifying possibility. Maybe our cosmos is far stranger and more lawless than we ever imagined. How many other impossible objects are lurking in our data, dismissed as measurement errors or statistical anomalies? How many times have we forced observations to fit our theories instead of letting them challenge our assumptions? The early universe suddenly feels like an alien realm, operating under different rules. Rules we're only beginning to glimpse.
And if the ancient cosmos could break our laws of physics, what other certainties might crumble under closer scrutiny?
The universe isn't broken. Our understanding is. Somewhere in the cosmic dark, 13 billion years ago, a black hole decided that our carefully crafted limits were merely suggestions. It grew impossibly fast, fed impossibly well, and left us a message written in X-rays and gravitational waves. You don't know me as well as you think you do. This is how science advances, not through gentle refinements, but through moments when nature grabs us by the shoulders and forces us to see reality with fresh eyes. The question isn't whether we'll find more rule-breaking objects. The question is, what other impossible discoveries are waiting just beyond the edge of our cosmic ignorance?
This is Beyond Revealed. Subscribe now and join us as we explore the mysteries that lie within our world and far beyond.